Okay, so this session is a preview of Module 15, Topic 4, Homework 1. I'll just go through question 1 here, leave the rest to you guys. So it's back to our story about the EPA and the exhaust emissions. I don't know why. In the last video, I got confused a couple of times and I was saying fuel efficiency that had nothing to do with it. I think I got the numbers right, but it's exhaust emissions, no fuel efficiency here. Okay. So the null hypothesis is that the mean is 1.45 grams per mile. The alternative, that the mean is less than that. And they're asking us to calculate the test statistic. Now, when this came up in an earlier exercise, the test statistic was Z, but this time it's T. What's the difference? Before, you were given the population standard deviation. One word changed in the story. This is just the sample standard deviation this time. So we don't know the population standard deviation. We can't work out the Z. The Z has a sigma over here in the formula for it. We don't have sigma. We don't know, so we cannot work out a Z score. This t-score is the next best thing. We're substituting the sample standard deviation in place of the population standard deviation. So we're using an S, not a sigma. And that changes the shape of the distribution a little bit. It's subtle. I mean, when I draw the pictures by hand, they look the same, but it's different. It's a different formula. All right. So the first thing is we have to calculate the t-score, and over here in the homework exercise, it's showing us how to do that. So let me just type that into Excel here. My X bar was 1.21. My mu from the null hypothesis, we don't know mu. This is only from the hypothesis. So I'm going to make a little note here. It's unknown because we do not have access to the whole population. Okay, and then so while the 1.45 was a high hypothesis, this is an actual fact, but just about the sample. As far as the population of parameters are concerned, the mu and the sigma, we don't know either one of those. We just have a hypothesis. And this one here, the sample mean, it's an actual fact, but just about the sample. Okay, so how do you calculate the t-score? Oh, and sample size here, let's see. N was 28. Okay, so now to get the t-score, we'll do parentheses, this minus that, over parentheses, S over the square root of N. This has the advantage that if I set it up this way and then I come to question 2, you see I can just change the numbers. I don't have to type the formula in, you know. I said, oh, in question 2, maybe it's a bigger sample. Just change it, see? Okay. So you can speed things up a little bit. Anyhow, I get negative 3.17 standardized units. And since the tables in the back of the book and so forth use their z-scores and t-scores to the nearest hundredth, that's what I do. But for my internal calculations, I'll always just click on the number over here to use all the digits. Okay, so calculate the p-value. So, got to draw the picture in order to know what to do. So in question A, they gave us the answer. In question B, we got that. For question C, find the p-val. I'm going to start out drawing my t-distribution. So if the null hypothesis was true, then when you calculate all these different t-scores over here from different people, go out and get different groups of 28 cars, different samples. They all get a different t-score, and this is how that's distributed if the 1.45 was really right in the middle of the distribution of x bar. Then you'd get this thing centered around 0, and if not, it wouldn't be. So here's the distribution of t, and now our t-score came down back here near the left edge. Negative 3.17. And to find the p-val, I'm going to shade the area and then calculate how much is that area. And the question where people mess up, it's always, do I go to the right or do I go to the left? The alternative hypothesis was that mu is less than 1.45. That's a left-sided. So I want the probability of getting such a small t-score. See, even if I did this calculation, let's say I'd gotten positive 2 or something, I'd still want the left area because it's a left-sided hypothesis. You don't even look at the number. That's not how you decide. You look here. Okay. So I use this t-dist function to get areas to the left. And I type in the sample size minus 1. Why they don't just subtract for you, I don't know. But this thing here, this is the number of what they call degrees of freedom, n minus 1. That's what you type into the tdist function. And so we'll get an answer. Back over here to Excel and get the number. But see, I don't want to type the 3.17. I want to click on the cell so I get the exact number. And then here it doesn't really make any difference, but I like to click instead of type, so then if I change something, it'll change everywhere. And then, oh. I typed an extra equals. I don't know what for. Oh, and then it's true. Yeah. That's the thing that says get me the area, not just the height. Okay. So now I got it. Let me fix up over here when I put in the answer. Go ahead and type that. So there it is. And as a percentage, the nearest 1/10 of a percent, it's about 0.2%. And that's it. So do we reject the null hypothesis? No, yeah, let's see. We're doing our test at the 1% significance level. Okay, so our alpha, where am I? Our significance level was 0.01. And you notice that our p-value came out to be less than alpha. So we reject the null hypothesis. Okay, so the EPA said, we think the mean's 1.45 grams per mile. You said, well, I got 28 cars and their mean was only 1.21 grams per mile. Looks like you're wrong. Looks like it's smaller. They say you just got lucky. Get 28 different cars tomorrow, you'll see. And you say, well, you know, there's only a 0.2% chance I would have got so lucky. So more likely your null hypothesis is just wrong. And they agreed ahead of time. They said, well, okay, if your p-value comes down less than 0.01, that'll be good enough. And it did, so you win. That's the way it goes. You need to set up that criterion, that alpha, before you get started collecting data. And if there is no level of evidence that would convince them, then don't bother to collect data, you know? Okay. But mostly there'll be some, they'll say, okay, well, 1/10 of a percent or whatever it takes, but at some point we're going to be convinced. Then they'll get somebody else to do another sample just to make sure they're getting, you know, the same conclusion. But otherwise, you'd never know when you're finished. Yeah. And just getting another sample is really not as good as getting one sample in the beginning that was twice as big. So, you know, so it's good to repeat this to have somebody else do it in case there was something wrong with your method, or in case they just don't trust you. You do replication of the experiment by other researchers. But there's no point having you necessarily do it twice if you're going to do it exactly the same way, because 2 samples of 25 is not really as convincing as 1 sample of 50, so you just do it all at once. Okay. All right, I think that's going to do it for this topic. I'm going to stop the recording.